Hello there, this is Alana Taki, and I've received a request for help with this problem, which is from section 5.4 for Math 133. This particular problem is number 33 in the study plan or in the textbook if you open it up. Where it happens to fall in your particular assignment, who knows? Okay, so I'm going to look at the example and do that one. So let's see here if I can make this larger. So we're going to determine the probability that at least 2 people in a room of 4 people share the same birthday, ignoring leap years, and assuming each birthday is equally likely by answering the following questions. Compute the probability that 4 people have different birthdays, and then the complement of 4 people have different birthdays is at least 2 people share a birthday. Use this information to compute the probability that at least 2 of the 4 people share the same birthday. Okay, so let me just pull this up right here. So let's begin. There's a few things that we want to kind of take note of in this setup. We're talking about birthdays and we're ignoring leap years and assuming each birthday is equally likely. So that means that when you start out, you assume that the probability of any given day is 1 out of 365. Oops, 365. So this whole business right here is just to get you that the first denominator has to be 365. So you're assuming only 365 days in a year. Every one of those days is equally likely, which is actually not true. First of all, there's leap years. And second of all, just due to patterns of behavior, sometimes babies are more likely than other times, hypothetically speaking, depending on the population that you're looking at. Okay, so we're going to start off with the 4 people. So we have 4 people sitting in a room, and I want to know the chances that they're all different. So you have the first person, the second person, the third person, and the fourth person. So let me draw that out real quick. There we have it. So I have the first person, the second person, the third person, and the fourth person. Now, there's an implied and in this problem because you want them to all have different birthdays. You want the first person to have a birthday and the second person to not have that birthday, and then the third person to not have that birthday or the first person's birthday, and so on. So since there's an and in the problem, it's going to be multiplied. I mean, anytime you're dealing with more than one event in sequence, it's going to be the multiplication rule. It's just a question of, are you going to use the general multiplication rule, or do you have the ability to use independent rules? Okay, so I want the first person to have their own birthday, right? So that's no problem. Everybody's got their own birthday. So the chances of, grab the first person, the chances of them having their own birthday is 1. Or if you like, it's 365 over 365, right? So they are their own birthday. They have their own birthday. Everybody's happy. Now, you want the second person to have a different birthday than that first person because you want all 4 people to have their own birthdays. So that means that there are 364 days left for that person to choose from out of the 365 total. Right? Notice the denominators are staying 365 because there are 365 days in the year, assuming they're all equally likely, no leap year. Now, this went down by 1, so we're using the general multiplication rule, right? What we're doing is we're multiplying as we go along the probability of the next event in sequence, right? And since these are dependent because we want them to be different, right? Forcing them to be different forces a dependency because whatever this person's birthday is, let's say the first person has a birthday of, I don't know, May 29th. So if the first person's May 29th, the next person does not have that day to choose from. All the other days are available. So there's only 364 days available to that next person. Now the third person cannot have either one of those days. So if the first person was May 29th and the second person is May 30th, just for example, then the third person can't be either one of those. So that means that they have, out of the 365 days possible, they have only 363 available at their disposal. And then the next person has only 362, and then so on and so on. So you would keep going however many spots over you need to go in order to accommodate this many people. All right, so then I would just multiply those, right? So you could, oh, and I better label this at the beginning. So this is the probability, oops, give me 1 second. There we go, I should have done that at the beginning. So we have the probability of all 4 different birthdays for 4 people, and then we have that all figured out down here. So then I'm going to grab a calculator. Now there's 2 ways you can do this. So one of the things you might notice Now you can just multiply this out on your calculator if you want to be boring about it. It's fine. But you might notice the denominator is 365 4 times. So that's really 365 to the fourth in that denominator. The top is something special, which we often do not cover in a beginning probability class, but in case you've ever seen it, it's something called a permutation. So we're saying out of the 365 total, we are going to choose 4, and there's an order to it, right? So there's 4 being chosen, and once you choose one, then it cannot go back in the mix, and there's an order to it. And you don't have to do it this way, but it does make it quicker to type into a calculator. So either way, we're going to have to go find it. So let's grab a calculator, shall we? Okay, so I'm going to clear this out. Now, just for fun here, I'm going to type 365 times 364 times 363 times 362. So with 4 of them, it's not that hard to type, but if you had like, I don't know, 10 of them, you might prefer the little permutation method, which I'll show you in a second. So that's the numerator. It's 1.74586E10, right? And some change. The denominator is 365 to the fourth, which I'll figure out in a second, but I want to show you the way to do the other method. So let me think. I think I type 365 first, then I hit math, go over to the probability menu, and it's number 2, NPR right there. And it says, okay, you want to, out of 365, how many do you want to choose? Well, I want 4 for my example, so I'm going to pick 4 and hit enter. And see, it's the same number. See? So if you have a larger number in your problem and you don't want to sit there and type 365 times 364, blah, 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 then you can just use the permutation notation. It's the same answer. Now I need to divide that by 365 to the fourth, which would be 1.77 E10. So 1.77489 E10. 77489. Yep. Oops, not 12. There we go. All right, and of course this is terrible, so we would just make a calculator do all of this. So you can go up with your up arrows and kind of grab old numbers and then make it divide by other old numbers. You can do it that way all at once. Or you could just redo it. 365 math, go to the probability menu, pick number 2, 4, and then go over here with the arrow because you got to get out of there, and then divide that by 365 to the fourth. There you go. Either way. So 0.983644. So that's my answer. 0.983644. Technically, it's approximation, so I'll put little squiggly equals, an approximation sign with it. And there we have it. All right, so let me go back and check the study plan. I should be able to check. Now, they'll probably ask for a particular number of decimal places. So they went with 4.9836, which is fine. So I could round it to 0.9836 as well as the next person. So if they ask for 4 decimal places, then do 4. All right. Now, the next part is actually not hard because we've actually done the hard work in part A, but I want to make sure you understand what's happening. So the complement, i.e. the opposite in the sample space. So if you don't have, let me write this out one second. So if you're in a room of people and you know that not everyone has different birthdays, it's a little bit of a brain teaser. So if they all have different birthdays, it means everybody has their own day staked out. But if that's not the case, if it's not that everyone is different, that means that at least 2 people, maybe more, maybe 3, maybe 4, maybe, whatever, maybe 2 sets of 2, but at least 2 people must have the same day, right? If we aren't all in our own little zone, our own little day, then somebody's got to be the same as somebody else. Right? So how would we find the probability of that? Well, the probability that at least 2 are the same is the probability, or 1 minus the probability that they're all different. All right. There we have it. So I've written this out in symbols now. So the probability that at least 2 people share a birthday is 1 minus the probability that nobody shares. But that would be 1 minus the probability that they're all different. That would be 1 minus 0.9836. Now it's 9836 in our problem. It'll be different for everybody's problem because it depends on how many people there are in a room. The more people there are in a room, the less likely it is that they will all be different, right? So if you have 2 people in a room, the chances of being different very high. But if you have 200 people in a room, getting them all to be different, that is much, much, much harder to come by. All right, so 1 minus that would be 0.01, oopsie, 64. Let me see if I did that right. So 1 minus that answer is 0.0164 if when you round it. And that was the answer they were looking for. All right, I hope that helps with that problem. That's actually a very common problem in probability. So, and it works the same no matter how many people there are in the room. It just changes what this combination of fractions up here will be, this permutation here in the numerator. But everything else pretty much stays the same. All right, I hope that helps. I'll see you back here for more tutorials.